Problem number 15 was asked, and the student was concerned regarding the substitution of variables, so of your lower and upper bounds of integration. So what I'm going to do is kind of walk you guys through this problem so that you can see the setup of it and see why it is the way it is, but then more importantly to see how the substitution works as far as the calculus is concerned. So what I'm going to do is let me move this over to the side here and kind of make this a little bit smaller so that we're not taking up too much room. Okay. Okay, so we've got at noon, Alicia starts walking down a road, and she starts at 5 miles per hour. And then her velocity decreases according to this function right here. So what we have is Alicia's velocity. So the velocity, you know what I'm going to do here, guys, so that we can see these both on the same page. Let me cut this out. There we go. Now we won't lose it every time I write. Okay, so the velocity of Alicia as a function of time, okay, is given by this equation right here. So that's going to be 5 over t plus 1. And of course, this function is only good for values of t that are non-negative. Boris, he starts walking, but he's a little bit further ahead. He's a mile down the road. Okay, so if you think about the road, here's this stretch of road. Okay. Alicia starts here at the beginning at 0. It doesn't matter whether you put Alicia at 0 or not as far as some of the problem is concerned, but we're assuming that she's starting at the beginning of the road. Boris is starting 1 mile down, so 1 mile ahead. Okay, so his velocity function is the same. It's going to be his position function that's going to be different. So his velocity function, so v of Boris, velocity of Boris as a function of time, is given by this new function, 3 over t plus 1. Now you might say, why don't they use v of t like I did here? Okay, well the reason is they didn't give this v a subscript of a. So if they used a v of t here again, you'd have v of t equaling to 2 different functions. And so that's just really sloppy problem solving. So we don't do that, okay? But I'm good here because I put a subscript of b. So this would be 3 over t plus 1. Now, what you need to find in order to answer these questions is you need their position functions. So, for Alicia's position as a function of time is equal to Alicia's initial position plus the integral of her velocity function Now here I have to be careful, okay? If I'm going to use t here, then my integral has to go from 0 to t, okay? Which means that I have to change this variable right here, this t and this dt. The other way of looking at it, now I'm going to leave it this way because they want s sub a of t, so I need to change this, but that's alright because remember that this is just a dummy variable, so we'll say vx dx. I could have used y here or z, it really is irrelevant. But the important part is that this guy right here matches this guy right here, because we want her position at some time t, which means we have to add up her velocity over, when I say add up the velocity, the area under the velocity curve over that interval from 0 to t. Okay, so these guys have got to match. Now there's some information in the problem where we can help solve for this. So we know that Alicia's initial position at time 0 is 0, and that's given to us down here. I don't like the way that 0 wrote. Now this, her velocity of Alicia as a function of time, well, it doesn't matter. That's a dummy variable again, right? So just remember that VA of something has got to be equal to 5 over that something plus 1. So we're going to plug that in here. We're going to use x as our variable. So that means VA of x is equal to 5 over x plus 1. So we want to integrate from 0 to t of 5 over x plus 1 dx. And of course that is her position function, her position as a function of time. So 0, we don't have to write that anymore. We need to, and this is the tricky part with the book, we need to find an antiderivative of this. So we're going to use substitution. So let me write that down over here. So this is kind of our side work. So we're going to use substitution to find the antiderivative. So we're going to let, it doesn't matter what variable you use here. Okay, I'll use m. Okay, we'll let m be equal to x plus 1, this guy down here. And so that means that dm is equal to the differential of m is equal to the derivative of this times dx. Well, the derivative of this is 1, so that's just 1 times dx, or dx. Another way of looking at this is, this is not the best way of looking at it, but it'll get the job done. dm dx in Leibniz notation will give us, now the derivative of this is just 1. And if I multiply both sides by dx, I get dm is equal to dx. Now again, really you should try to avoid maybe thinking about it that way. And that has to do with how we set up the definition for the derivative, not necessarily whether this is actually true, okay, when you're dealing with infinitesimals or not. Okay, so but this is true. The rate of change, the dm, the infinitesimal change of m is equal to the infinitesimal change of x if m is equal to x plus 1. Okay, so this guy is going to help replace in here. So what I have, so again, this is gone. I have the integral, and I'm going to talk about my bounds in just a minute. But this is going to be 5 over, now m is x plus 1. So this is 5 over m, and dx is dm. Now here's the hard part. The bounds, the lower bound and the upper bound for integration change. They're no longer 0 to t, okay? Because we've changed this here. Now, if we want to go ahead and we want to change them, right now we can, okay? Or we can leave them and just note that that later we've got to go back and change m into x. Give me 1 second. So what we have here is we've got, in this one, we've got x. The x variable ranges from 0 to t. So x starts out here at 0 and goes up to t. So x starts at 0 and goes until t. Well, m is equal to x plus 1. So that means, okay, that x can be replaced with m minus 1 here. So m minus 1 is equal to x, which means m minus 1 starts at 0. I don't like the way that wrote. Starts at 0 and goes until t. So m, if I think about the bounds of integration here, from 0 to t, okay, m minus 1 goes from 0 and m minus 1 goes till t. which means that m has got to go from 1 to t plus 1. Like that. Okay. So let's find an antiderivative here. Well, we can pull the 5 out. I switched colors on us. Let me go back. So we're going from 1 to t plus 1. Pull the 5 out. We have 1 over m dm. And 1 over m dm is 5 times the natural log of m evaluated between 1 and t plus 1. So this is going to be 5 times the natural log of t plus 1, okay, minus the natural log of 1, which is 5 times the natural log of t plus 1 minus 5 times the natural log of 1. So that's going to be Alicia's position function at time t. Whoops. Okay, so let's go ahead and her position function at time t. Now, there's another way to go about doing this where we don't have to change the bounds. So let me show you another way. Oops, sorry, hang on. There we go. I'm going to draw it right over here. So when we get to this spot right here, instead of going down to here, let me just show you kind of maybe a little bit faster way of looking at this. So this is what we had for our problem. I'm going to find the integral of this, and I made a substitution. I'm going to make the same substitution. I'm going to let m be equal to x plus 1, and again, dm is equal to dx, like that. So I'm going to make my replacement in here. So this is going to be the integral. This is 5 over m dm, and so that's going to be 5 times the natural log of m evaluated between 0 and t. But here's the problem. For m, these guys right here are for x values, not for m values. So let's switch. We know what m was equal to. It was x plus 1. So that'll be 5 times the natural log of x plus 1 evaluated between 0 and t. Now when I do that, I get 5 times the natural log of t plus 1 minus 5 times the natural log of 0 plus 1, which is 1. And so it gives you the same value over here. Now, usually this is how I'm doing it in my head when I'm working through it, but this is really the correct way of working through it. So this is how you get her position function. Now you got to do the same thing for Boris. But Boris, okay, Boris here, I think I had him in green. Yep, Boris is in green. So Boris, his position function is equal to his initial position plus the integral of his velocity. Now again, I'm going to switch from t to some other variable. Okay, this is what I need to find. Well, what do we know? We know that his initial position where he starts is 1 mile. We also know that his velocity function is 3 over t plus 1. Okay, but I need it in terms of x. So okay, perfect. Now we need to find an antiderivative for this. So this is going to be 1 plus, again, by substitution. Okay, and the same process up here. We're going to end up with the following. we're going to end up with 3 times the quantity of the natural log. Okay. Well, I'll write it all out. You can follow the same steps up here, but this is going to be 3 times the natural log of t plus 1 minus 3 times the natural log of 1. Now all we got to do is to figure out when their positions are the same, if they do run into each other, take this guy and set it equal to this guy, and you'll figure out at what time their paths cross. Okay, so you got to use a little bit of algebra here. You know, you're going to get natural log is equal to something. You got to use the fact that the natural log and the exponential are inverses of one another, and you can work through this. But I think this describes over here, this really gets at the heart of the question that was asked, is why is there this substitution in there? And that's the case.